on the high-resolution luminescence spectroscopy and show you our last works about this theme. So our institute, Institute of Spectroscopy of the Russian Academy of Sciences, placed near the Moscow. It's a town Troitsk. It's also Moscow now, but nevertheless, you see we are almost in forest, and this is really good for the health. I don't know. I know that you see Fairfield Symposium should located in Troitsk, but now it's in Fian. But here it's also a very good place for the conference. There is a head of our bosses. Viktor Zatkov is the director of our institute. Andrei Naumov is a head of department of the condensed matter spectroscopy. And Marina Popova, a professor, all of these professors, of course, head of the laboratory of Fourier spectroscopy. There is our equipment, our main device, which we use for our experiments. We have a wide collaboration. Here is our laboratory. We have a wide collaboration, not only with Russian laboratories and universities and institutes, but also with all world, from France, Italy, Poland, United States, Netherlands, and so on. The research area of our laboratory is the spectroscopy of materials for optics, optoelectronics, photonics. We're also working with magnetic systems, low dimensional and frustrated magnets, multiferroics. One of the big part of our work is a study of phase transitions of different natures. It can be ferroelectric, magnetic, structural, quantum phase transition, so by the optical methods. And as well, we are working with all kinds of interesting optical materials, semiconductor, superconductor, quantum dots, phosphors, as well as other promising materials for various applications. We are using the methods according to the exact science problem which we investigate. So the main, our research method is an absorption spectroscopy in wide spectral and temperature range. But also we are working with a Raman, attenuated total reflection spectroscopy, reflection spectroscopy, terahertz spectroscopy, polarimetry, spectroscopy of materials which placed in some external fields like magnetic, electric, or maybe in some strain. Photoconductivity spectroscopy measurements, and relatively new method, it's a high-resolution luminescence spectroscopy. What's the difference between the absorption spectroscopy and luminescence spectroscopy? First of all, the luminescent have much higher sensitivity because we register only useful signal. From the first point, we have the second advantage, ability to work with microsamples, small samples, powders, and the crystal with single sensors as well. Also, we have ability to separate optical centers, so-called site selective spectroscopy, using different excitation of the wavelengths or, for example, X-rays. Also, we can investigate the transition between excited levels and investigated the fine structure of the ground state structure of ions, for example, rare earth ions at low temperatures. But in fact, absorption and luminescence spectroscopy complement each other. So it's really good to use these two techniques for understanding some materials properties. Okay, why not working? Yeah. For this purpose, for investigating the luminescence spectra, the luminescence vacuum model was built. Nikolai Boldyrev calculate the optical scheme, a high throughput optical scheme to register the optical luminescence. We have three kinds different excitation for such a geometries. It's a geometry of backscattering on the side and through the sample. And this model was connected to our high-resolution Fourier transform spectrometer, Bruker IFS 125. So it works in the spectral range from the terahertz to the ultraviolet and very wide. And also we can investigate the luminescence in this region too. And with a resolution up to 1,000th wave number. We also can cool down our samples up to 2.5 Kelvin using the closed cycle helium vapor cryostat. We have several cryostats, but this is the last one, the much power than before. And for the excitation of the luminescence spectra, we can use titanium sapphire laser with a doubler, as well as series number of diode laser. And our opportunity of the excitation is X-rays. So we can excite the luminescence by the X-rays. So here is a scheme of our luminescence setup to investigate the luminescence in the magnetic field. We built self-made magnetic system, which placed into the cryostat. And also we built the module for the registration of the optical luminescence signal. And we can use different kind of detectors to register the luminescence signal. It's like indium antimonide, indium gallium arsenide, silicon photomultipliers, bolometers, and so on. So to show in our opportunities of the built setup, we take the well-studied model crystal, namely double lithium yttrium fluoride with rare earth. This crystal have a lot of applications, such as solid-state laser crystals, scintillator, phosphors, and promising material for quantum memory and for laser cooling. Namely, we take the crystal with a holmium ion because before in our laboratory by Marina Popova and Nikolai Gladze, these crystals was widely investigated, and here you can see there is a resolved hyperfine structure are observed. You see this work very old. It's from previous century, 1985, 1991, and rarely relatively new work in 2004. As well, by Marina Popova and Nikolai Gladze, was observed a isotopic structure because of the lithium isotope disorder. So there is a lithium-7 crystals, lithium-7 with small concentration of lithium-6, and lithium-6 with small concentration of lithium-7. So it's a structure in structure. 3 years ago, we built our magnetic system and investigate the spectra of these crystals in the absorption spectra. So there is a magnetic field, there is a wave numbers, and there is a color map of observed hyperfine levels. And for the first time, we observe directly observe the anti-crossing in the optical region. So there is a 2 micron, but we observe such a picture in the visible region too. And this work was published in 2019. Here you can see the high-resolution luminescence spectra of this crystal. There is a lot of transition, much more than in absorption spectra, because we observe not only transition to the ground state, but between the excited multiplets. So there is a scheme of our observed spectra. And in this spectra, we, for the first time, observe the resolved hyperfine structure in the luminescence spectra of a crystal. You see really good spectra. As well as for the absorption spectroscopy, we observe the isotopic structure in the luminescence spectra as well. And what's interesting and surprisingly for us, in the luminescence spectra, the line width of observed hyperfine structure are much narrower. So 10 magnitude narrower in absorptions. The absorptions in the absorption spectra, the narrow lines are 15,000 wave number. It's around 450 megahertz. But the narrowest lines in the luminescence are 10,000. It's 66 megahertz. So there is a narrowest luminescence which observed from the ensemble of atoms in the crystal. The next thing we observe in the excited states level, very good picture of anti-crossing. As well, we observe the fine structure in the anti-crossing because of wave mixing of different states. And also we observe a splitting because of random lattice deformations, which can be used, for example, for quality control of the crystal. I told about this picture. So there is a superposition of the wave function in the antiferromagnetic anti-crossing point, sorry. The next thing, we observe some very interesting shape of the luminescence spectra in the magnetic field. You see, we named it like bugs or some structure with wings. And the first time when we're looking on this picture, we don't understand what's the matter. But when we calculate the spectra with a wave function intermixing effects, you see we have a really, really good explanation of such structures. This work will be published in Journal of Luminescence. This is not only in submitted. So, what's the possible applications of the observed effect? First of all, it can be used for quantum memory because when we tune the magnetic field in the anti-crossing point, we can produce a very good structure for the three-level lambda system. The next one, anti-crossing at the delta m equals to 0. It doesn't matter. It's about the deformation splitting. We can check the quality, quantum quality of the crystal. It's very good for using and for checking the crystal. What is the quality, not crystalline quality, but the quantum quality. The next thing, we observe some lines which have very narrow, you see, very narrow lines with very big G factor at around 20. And it allows us to build the optical magnetic field quantum sensor with a resolution up to several microtesla. So for building such a device, we do not need big, slowly and very expensive Fourier transform spectrometer. Because we're using only one line, we can use scanning Fabry-Perot. It's rather cheap, and the luminescence in the telecommunication wavelengths, so we can use fibers, ordinary fibers for the collecting the light from the crystal. There is another example of using our setup. We are investigate the silicon vacancy centers in the CVD diamonds with different silicon isotopes. And here we observe the narrowest luminescence lines from assembly of silicon vacancy centers. So you see there is a different isotopes. It's an isotope shift with a different silicon 28, 29, and 30. Also, we investigate the color centers in silicon carbide. Also, really very, very narrow lines, which also can be used, for example, as quantum sensors of magnetic fields or strains, or some single photon emitters. Next example, we are observed the deformation splitting in the optical spectra of perovskite lanthanum aluminum O3 with a rare earth holmium and thulium. We observe the deformation splitting due to the random strains at the boundaries at ferroelectric domains on these domains. This is our new publication too. So here you can see our cave works on the high resolution luminescence spectroscopy. You can take picture of this slide, and all these works are open access, and you can read it if you have some interesting in such investigation. So one more, our capabilities. It's high resolution, wide range luminescence spectroscopy in very wide spectral range, temperature range, magnetic field. We can also apply it electric field and different excitation, as well X-ray excitation too. High resolution, wide range photoconductivity, Raman spectroscopy, and absorption spectroscopy. So here you can see there is a X-ray tube, and there is a diamond with a nitrogen centers emit light, and we also investigate such a system now. There is a cryostat with also X-ray tube inside. So in the conclusion, I want to tell that we are open for cooperation. We are searching for the interesting crystals, interesting system to work with the high resolution luminescence spectroscopy, you can write me or Marina Popova, or also can use my visit card by QR code to connect with me if you have some interest in our equipment. Thank you very much.
Yes, thank you, Kirill. Thank you for presenting the examples what can be done in our laboratory in the field of high-resolution spectroscopy. And it is the main part of the modernizing the setup has been done by Kirill. So please, does anybody have some questions? Вопросы, может быть?
Hello, Kirill. Thank you for the interesting presentation and for the fantastic opportunities that now you have in your laboratory. I have a question about, I usually working with semiconductor nanocrystals in the solutions or in glasses, so in some dielectric matrix. So in semiconductor nanocrystals, also there are a lot of phase transitions. So depending on the type of the nanocrystal, there can be like 10, from 2 up to 10. And the main way to see these phase transitions in optically is not the luminescence spectra or absorption spectra, is luminescence excitation spectra at different temperatures. Is it possible at your laboratory to do this? Not luminescence, but excitation spectra of the luminescence.
Yes, it's possible. But why only excitation spectra? Why not luminescence?
Because
there is a wide broadband spectra.
Yeah, usually the luminescence spectra is quite broad because we usually have the size dispersion of the crystals. Of course, that's why absorption spectra and excitation spectra are also broadening. But the luminescences usually in these systems have excitonic nature, and that's why we have a lot of excitonic transitions.
Excitonic transitions are relatively narrower.
They're related to the size and to the crystal structure of the crystal, so we can see the
of course, it's possible.
Thank you.
Any questions?
Any more questions?
There is a question.
Thank you for the interesting talk. You say about possibility to get a lambda scheme.
Yeah.
What about the lifetime of low frequency coherence in this?
We do not do this experiment. We just show the opportunity to build using the scheme. But really, we do not use it because of the fluoride crystal. The fluoride crystal are bad for the quantum memory because of the magnetic moment of fluoride. But we can use this technique for different kinds of crystals, not only fluoride crystals, but
okay. Thank you.
So it's just an opportunity to measure, showing our opportunities. Any question? No? Okay. Marina Nikolaevna, there is a no question.
Yes, thank you very much. And let us thank the speaker if there are no questions.
Thank you.